try to solve Leetcode problem 2581, count number of possible root nodes. So for this problem, we are basically giving edges. So this edges means a tree structure. So for the tree structure, we have many edges like that. And we also have a gases. So this gas means for any edge, for example, this edge 1 and 3. So it means from a root node is 1 to another node, it is 1 and 3 for this edge. So if it is inside my edges for the tree structure while I build it, so this 1 and 3, it can also be 3 and 1 inside the edges because it is not it is an unidirectional graph. Yeah. So if this 1 3, for example, is inside my tree structure, this is the root and this is the child 1 3 inside, and this 0 3 is also inside the root to its child, its parent to its child, and also 2 and 4 parent to its child. Yeah, it exists, so it means the root 0 is 1, so we're gonna count by 1. And similarly for others, root 1 and 2, there are also more than and equal to 3 gases, 3 edges inside the gases, so we're gonna return a 3 because for root 3 and 4 there are only 2 count. Yeah, and you cannot find more than 2 count, so this is why we're gonna return a 3. Yeah, let's analyze this problem first from the whiteboard. After that, I'll go to the code editor to finish the coding. Yeah, for any kind of the tree structure like this, so for example, and we also have a gases. Let me put a gases here. And inside gases, I'm gonna turn the gas array into a set. Yeah, because for the set, when I check the edges, it's gonna be just O1 times complexity. So I'm gonna prepare all the gases inside a set. Now I'm going to check the structure. So while I'm building the tree, I have a structure can be any one of them. So for example, for the first structure, 0, 1, 0 is the root, and then to its child until to the leaf node, like 3 and 4. Yeah, I'm gonna check the edges one by one. So for example, I'm gonna loop through the tree like this, 0 to 1, 1 to 2, 2 to 4, and 1 to 3. And I'm gonna check the gases at the same time. Yeah, for example, if I have a gas of 3, for example, I have 3 edges inside my gases set. So I'm gonna have a result of 3. So for the next step, what I'm gonna do? Do I need to check this also? Yeah, I'm gonna loop through from 1 and check all the edges. So for this one, it's gonna be the time complexity of n squared. N is the number of specifically it is e plus v square. Yeah, because we're gonna check all the nodes one by one. But for this kind of situation, it's gonna be time limit exceeded. Yeah, because n will be 10 to the power of 5. It's gonna be very big number. So we have to, calculate it by O(n) time complexity. It means O e plus v. It's gonna not be have a square. So how can we solve it? So we can use the existing data before. Yeah, so for the first one, while we are checking the root node 0, we got a count of 3. We're gonna have a record of this 3. But for the next step, we don't need to check one by one like the brute force. We can directly change the root from 0 to 1. Why it works? Yeah, because even we change the edges of 0 to 1, we change the root, the structure didn't change. Yeah, let's say currently our root is 0. Yeah, and we have a structure like this. Now we're gonna change the root. So this one gonna be 0. 0 will be the child of 1. So 1 will be the root. Did we change the structure of 1 to 2, 1 to 3, and 2 to 4? No, we didn't change. It means only 0 and 1 change the structure. Yeah, it means we don't need to take care of all other situations or other relationships. We only need to take care of 1 to 0, 0 to 1. And for 0 to 1 and 1 to 0, it's easy to check. We just need to check if 1 to 0 is inside the set or 0 to 1 is inside the set. we can just use mathematics to easily calculate it. Yeah, because from the beginning, if 0 to 1 inside the set, we're going to have a count by 1. Now we are going to change the root. If we change the root, definitely we're going to minus 1. Why? Because 0 and 1 is inside the guess set. Yeah, and now we're going to plus. This means 3 minus 1. Yeah, now we're going to plus 1 to 0. 1 to 0 is inside the set or not. If it is inside the set, we're going to plus 1. So it's going to still be 3. Yeah, so if 1 to 0 is not inside the set, we're going to plus a 0. So it means the final result is going to be 2. So it will be less than my k. K is 3. Yeah. So I will not count it. If it is more than 3, I'm gonna count it is 1. So it means after first DFS, I'm gonna use another DFS to check the count. Even I use 2 DFS, but the time complexity is still O E plus V. This is why it works. Now let's go to the code editor to finish the coding. As I explained, I'm gonna prepare a graph. So the graph would be default dict. Inside, I'm gonna prepare a adjacency list. You can also prepare a set, but a list is faster because there's no duplicate inside the adjacency list for the graph. Now I'm gonna prepare the graph. So for UV in edges, so GU should append the node V because it is a unidirectional graph. So GV can also append the node U. Yeah, this is the first step for building the graph. So after that, I'm gonna prepare a guess set. Yeah. So the guesses should still be the same. I'm gonna prepare a set because the array cannot be used as an element inside the set. I have to turn it into a tuple. So inside it's gonna be a tuple UV. So for UV in guesses. Now I've prepared the adjacency list and the guess set. Yeah. After that, I can use the DFS. From the beginning, I'm gonna prepare a self.count. Yeah. Basically, this self.count is a global variable because inside my DFS, I'm gonna use this variable. So this is why I prepare a self.count. Now I'm gonna define the DFS. Normally, I'm gonna use a visited set, but for this kind of a problem, the easiest way is to use a node with parent variable to check to avoid the duplicate. To avoid the duplicate node, it means the node can just go down to check to traverse all the node, all the edges. I don't need to go back. This is why I prepared a parent node. So from the beginning, the parent node should be, let's say, the node, I can prepare any node, but normally for for easy initialization, it's gonna have at least one node, maybe 0. Yeah, the node would be at least 2, but I'm gonna prepare the first node as 0. Yeah, you can also prepare a node 1, it doesn't matter. Yeah, but now I'm gonna prepare a node 0. For the parent node, from the beginning, for node 0, if this is my DFS, this is my root node, so its parent should be a -1. You can also prepare any values not inside the node. You can prepare a -2 or minus anything, but not inside this node. Now what I gonna do, I just need to, let me put the self.count here, because inside the DFS, I'm gonna write the function. Yeah. So after call DFS, basically I can get the number of count for the first one. And for others, I can use another DFS. Yeah. So for the next DFS, I'm gonna prepare a result from the beginning, and I'm gonna call it I'm gonna call it count root, because for the second DFS, basically I want to count the root. Yeah. Let me first prepare the first DFS. After that, I'm gonna prepare this count root. Finally, I just need to return the result. Let me first prepare the DFS, for the first one, check from the root start as 0. So for the basic DFS, we just need to check one by one. So for, let's say, for neighbor in G node, for the DFS traversal, it's gonna be easy. We just need to traversal from the 0 to our other node. We're gonna check if this neighbor not equal to parent, because we don't need the DFS to go back. We need to check all the edges at all the node. If neighbor not equal to parent, we can use the DFS of what? Of neighbor with my node, because currently neighbor is my current node, and this node gonna be the parent. But inside I'm gonna to count how many of them. So if my node with neighbor, if this tuple is inside the guesses, so the self dot count should be +1. And now I'm gonna call this function DFS 0 to 1. Basically, after call this function, I'm gonna get a number of 3. For this example, from the root 0, I'm gonna get a number of 3. And now I'm going to use the second count root. And this is a basic structure of count, not count root. I'm gonna change it to change root. So because this function is basically a change root DFS, after change root, I'm gonna check one by one if it is more than or equal to k. So now let's write the change root function from here. It's gonna be exactly the same from here, but from the beginning we're gonna have a check. If self dot so here inside the change root, let's do some preparations. It still be the same node and parent, but inside I'm gonna have a count. Because I'm gonna use this count as my dynamic programming. Basically, this is a tree DP problem. And where is the DP from? It is from this count, because I'm gonna use this count each time. This is my DP. So if this count is more than and equal to k, so the self dot result should plus equal to 1. After that, after all, I'm gonna call this change root function, and inside it's gonna still be the same from 0, -1, and the count. The count should be the self dot count. So from the beginning, my parent is still, my root is still 0 and parent -1, and I have a self dot count. It is 3, as I explained earlier. So if it is 3 for the beginning, if it is more than this equal to this k, it's gonna +1. So this is why I'm gonna have this line. And after that, I'm gonna check all by I'm gonna check all the edges if I change the root. For example, from 0 to 1, if I change it. So what? So now 1 is my root. So what about I change 1 to 3? Now 3 will be my root. So what about 1 change to 2? So 2 will be my root. And if I change 2 to 4, 4 will be my root. So this means basically I change the root of the graph, but I didn't change the structure of the graph. The structure of the tree will always be the same. We just say it, 0 is the root, but any node can become the root, because it is a tree structure. Inside it, any node can become the root. We just change the root, but we didn't change the tree structure. Now let's check. Basically, I need to copy the code from here. Because basically it's the same. We just needed to use another DFS. So if neighbor not inside the node, if neighbor is not parent, so I can call the DFS, so that I can call the change root. Inside, it's gonna still be the same with neighbor and node. Now, I'm going to prepare the DP. So DP is the count. How should I prepare the dynamic programming of this count? Yeah, as I explained earlier, we just needed to change the answers. If this answer is inside the gas, we're gonna plus 1. If it is not inside the gases, we're gonna plus a 0. Yeah. So from the beginning, it is a count. We're gonna minus the previous adds. For example, it is a 0, 1. So we're gonna minus the previous adds. But for the previous adds, we need to check if this node and neighbor inside the gases. Yeah, this means if it is inside, we're gonna minus 1. If it is not inside, we're gonna minus a 0. Now we need to plus our new adds. Yeah, because if we change the adds, yeah, we change the root or we change this adds, we change this adds, we're gonna minus the previous one and plus the new one. So the new one we just need to copy. Yeah, copy it. And change this neighbor with node. Because currently this neighbor gonna be the root and this node will be its child. Yeah, basically this is the entire code. Yeah, everything from here and here, it's template. Yeah, from here basically, and only from here and this line, it may be the new line of the code to find how to change the root. Yeah, now let's just run it to check if it works. Default dict. Is there a there is a typo. Yeah, as you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it passed all the testing cases and it's pretty fast. And now let's analyze the time complexity a little bit. As I explained earlier, the number of nodes will be 10 to the power of 5, and the number of answers will also be n-1, 10 to the power of 5. So it means the time complexity is O(n). So n is the number of edges or the number of vertices. Basically, it is O to n, but for the big O, it is still O(n). And even we use gases, but we turn this into a set. So if we check an edge inside a set, it is O1. So it didn't increase the time complexity. And the space complexity is O E plus V. E is the number of edges. V is the number of not vertices. But for this E and V, it will still be n. Yeah, because it's the same. It's a sparse graph, so it is still O(n) for the time and space. Thank you for watching. See you next time.